Good afternoon. It's my pleasure to welcome you to this lecture, one of many events scheduled to celebrate and welcome Dr. Samuel L. Stanley, Jr., an accomplished educator, medical practitioner, and researcher as the 5th president of our university. I've done this a number of times already this week, and it's my pleasure to do so once again. Before coming to Stony Brook, Dr. Stanley served as Vice Chancellor for Research at Washington University in St. Louis. He received his BA from University of Chicago and his MD from Harvard. He completed his internship and residency at Massachusetts General Hospital and moved on to postdoctoral work in immunology at Washington University. Thereafter, he was appointed to the faculty in the Division of Infectious Diseases of Washington University's Medical School, one of the nation's highly ranked schools of medicine. He has an outstanding reputation as a distinguished medical researcher and has published extensively. Under his leadership and guidance as Vice Chancellor of Research, Washington University's sponsored research funding reached nearly $600 million annually, a very impressive figure. In addition to his impressive medical research credentials, those of us who have been working closely with him over the last couple of months are equally impressed with his understanding of and his commitment to all of the elements that make a university great. He embraces the totality of the academic discipline, from the letter disciplines and arts to sciences and medicine. And he will help us lead Stony Brook's efforts to build upon the foundation of our critical relationships with Brookhaven National Lab and with Cold Spring Harbor to achieve what we hope are going to be our next generation of successes. Dr. Stanley is an articulate, thoughtful, deliberative speaker, and he is strategic in his approach. He embraces a leadership and a management style that empowers people to do their jobs. It's a very exciting time for Stony Brook University, and I'm sure you join me in looking forward to Dr. Stanley's tenure and are confident that his presidency will bring many new and forward-thinking opportunities to our institution. Thank you again for joining us in celebrating this historic occasion for our university and our new president, and it is my pleasure to welcome President Stanley to the podium.
Well, thank you very much, Brent, and I do appreciate the introduction. He has given it several times before, actually, because it sounds very familiar, but I love hearing it each time. But enough about me. This has been a fantastic inauguration week, and one of the things that's really been a highlight, and I've said this before, has been the opportunity to really hear about the amazing work that's going on from our faculty. And this presidential lecture series has been one that I've enjoyed thoroughly. It's spanned the gamut of the kinds of activities we have at Stony Brook, but I've been singularly impressed by the scope of our activities and really the quality of the work that's going on from our faculty. So we're not going to be disappointed today, and I think this is going to continue in the same vein. We were very fortunate just last year to have engaged the mathematician John Morgan to be the founding director of the new Simon Center for Geometry and Physics. John was formerly chairman of mathematics at the mathematics department at Columbia University. He's really a distinguished and internationally recognized scientist. He was elected to the mathematics section of the National Academy of Sciences in 2009. In collaboration with other mathematicians, he's written advanced treatises in 6 different areas where mathematical research was breaking new ground, often while events were still unfolding. Each of these works was said to have substantially advanced the state of the art in the field, and at the same time gave a powerful impetus to future research by creating a mathematically solid foundation and framing out where new developments were needed. John is really well known for the clarity of his thinking and for his patience in pursuit of complete understanding. We are very fortunate to have someone, I think, of John's caliber to really set the tone for the new Simon Center, and I think he's really going to set an incredible foundation from which we can build upon. And under his patient and clear-sighted leadership, I think Stony Brook is going to benefit greatly, and this will be a benefit to geometry, to physics, and to really all the rest of science. So I'm very honored indeed to introduce one of the newest members of the National Academy of Science and a wonderful addition to Stony Brook's faculty. Please join me in welcoming John Morgan. And I should say his title is Why is Center for Geometry and Physics?
Thank you very much, Sam, for that introduction. I've only heard that once, but I enjoyed hearing it, and if you would like to give it again tomorrow, I would be happy to come and listen again. I'm very, very pleased to be here today to participate in your inauguration ceremonies. This is a great moment for Stony Brook. This is a very challenging time, but it's a very exciting time, and your leadership as we go forward over these next years is going to be crucial. And I have every confidence, as Brent and other people do, that this will be an incredible time for Stony Brook. I'm very, very happy to be here, to take part in it, to help lead the Simon Center as it goes forward. I couldn't resist the invitation to come today and tell you about the Simon Center. It's this building going up out there, which I'm sure many of you have seen, and I imagine you have wondered what's going to happen in that building. What is the Simon Center about? Why do we have a center for geometry and physics, and what do geometry and physics have to do with each other anyway? Well, today I'd like to try to answer, or at least partially answer, some of those questions. And I thought I would begin with the physical, the construction of the building, a little bit about what the building is going to look like when it's finished, then some programmatic descriptions of what's going to go inside this building, what sort of people, how many, what we expect them to do. But then the main part of my talk, the real core of the talk, is to try to explain the intellectual context and rationale for a center in geometry and physics. So as I said, I thought I would start with the construction, and I wanted to show you what we in the Math Tower have been watching unfold over the last, how long has it been now, 6 or 8 months. So I've got a time-lapse movie here, which I can't seem to move up. So this is a picture of the construction of the Simon Center, 5 pictures a day rolled into a movie. And one thing that's quite striking about this, besides the fact that the computer stops ever so often because it doesn't have enough buffering to actually run the movie, is how much of the construction time is given over to digging the hole and laying the foundation, which we're just beginning to do here. So they pour all this concrete, all gets covered up. So this has been from April until essentially now. What you see on the lower left, down here, it will be a large auditorium. I'll talk more about that in just a minute. So now they're above ground. Steel floors, more floors. And then the very top of it. There it is. That's what it looked like maybe 2 weeks ago. I haven't updated this picture since then. But when it's finished, let's see now. I've forgotten what I'm supposed to do. I'm supposed to minimize this and open up this. As you can see, I'm somewhat technologically challenged. So here we have the title, why a Center for Geometry and Physics. When the building is finished, it will look something like that. A glass curtain wall on the south-facing side. Just to orient you, what you see over here is the existing mathematics tower, and that direction is west. So this is a south-facing glass wall, a curtain wall. The auditorium that I pointed out to you in the construction is down here, large 250-person auditorium. The building is divided into two sections. The lower two, well, there's a basement and then a plaza level here and a second floor here, which we think of as public space. The plaza is a natural entrance to the auditorium. Off the plaza, there will be an exhibition space for art. On the second floor, there will be a cafeteria or cafe that will serve lunch to the members of the center and other assembled Stony Brook masses. The third, fourth, and fifth floors are the offices. So we'll have, when all is said and done, roughly 35 offices for faculty and then another 8 or 10 for staff. The faculty will, well, there will be a permanent faculty, a director, and 6 other permanent members, of which we have hired a director, yours truly, and 1 permanent member, Mike Douglas, a physicist. I don't see him here. I guess he's coming later. We will eventually have 6 permanent members. We'll have postdocs. The current plan calls for 12 postdocs. These are 3-year positions. So we'll hire 4 a year, 2 in physics, 2 in math. In addition, there will be visitors to the center. At any one time, roughly 18 visitors. Some will stay for a semester, some will stay for a year, some will stay for a month, some will stay for 2 weeks. So there'll be a flow of people through the center, varying lengths of duration. In addition, we'll run focused workshops, we call them, at various times during the year. There's been, for quite a while, a long summer workshop headed by Kumran Vafa from Harvard, which I think served as the model for this center. It was a summer workshop, month-long summer workshop in physics. We will continue to have that, and then during the academic year, we'll have workshops when we bring in 20, 25, maybe 30 people in a concentrated area for a week or maybe 2 weeks to really focus on exchanging information in that area. So that's the programmatic activity that will go on inside the center. But what I really want to talk about is, as I said, the intellectual rationale and context for the center. And this, of course, has to do with the relationship between geometry and physics, or more generally mathematics and physics. And there's been a long history of interaction between these subjects. I won't try to trace it all the way back to its roots, but I will try to give you some historical examples of the interaction. Turns out in the last 25 years or so, well, maybe 30 now, there's been a completely new and different, a twist to this interaction that's been unlike anything that we've seen before. And this twist and this new form of the interaction has led to some of the central questions and mysteries in both physics and in mathematics, mysteries that are driving the subjects, both subjects today, and for which no one really has an explanation. And that's the context in which this center will exist. I forgot, this is the lobby level. I should have shown you that earlier. So this is the plaza or lobby level. The second floor you see off here on the right. The cafeteria will be right in there. The art exhibition space in here. And this is the, let me see. Okay. So I want to try to give you some examples of past interactions of mathematics and physics. Then I'll try to describe briefly from the mathematician perspective what physics is all about, or at least the part of physics we're concerned with. Then I'll get to what's probably the most difficult part of the talk. That's what mathematics, and in particular geometry, is about. And then I'll get into the relationship the current relationship between the two subjects, and try to give you a sense, as much as I can, of how the relationship has changed and what the new questions that are coming out of this new relationship are, and some of the things we hope the center will address. Okay. So I decided to start my example between interactions between mathematics and physics with Newton. So Newton was studying gravity, and in order to study gravity, he had to invent something called calculus. So gravity, as Newton presented it, had two features to it. One was his famous law, F equals ma. Force is equal to mass times acceleration. So the way we're going to think about this equation today, force is going to be given. That's the second part of what Newton did. He was studying gravitational force. M, mass, is how much stuff you have. It's A that's interesting for this part of the discussion. A stands for acceleration. So what is acceleration? Acceleration is the time rate of change, the rate at which velocity changes, the time rate of change of velocity. What's velocity? Velocity is simply the time rate of change of position. Okay. But it turns out, to make sense out of this notion of time rate of change or instantaneous time rate of change, one needs to extend beyond the obvious into the mathematics of calculus, taking limits. So let's think about what velocity is for just a minute. You're driving a car and you say, in the last hour I went 60 miles. So I'm going 60 miles an hour. Of course, that's a gross approximation to the truth. You passed some people and you sped up, and maybe you were going 90, and then you saw the cop and you slowed down to 50. And so you didn't really go 60 miles an hour. Over the hour, you averaged 60 miles. Well, we get a better approximation to our speed at any time if we say, well, how far did I go in a minute? And then multiply that by 60. Well, that's still an approximation. You could have passed somebody in that minute. That might have been the minute when you saw the cop and slowed down. Well, okay, nothing to stop us from replacing a minute by a second. Let's see how far we go in a second and multiply it by 3,600. Usually in seconds you would measure the distance in feet. So let's multiply by 3,600 and divide by 5,280. Because there are 3,600 seconds in an hour, and there are 5,280 feet in a mile. And that would give us our average speed over a second. But it's still an average speed. Now, in a second, a car can't change velocity too much, so it's a pretty good approximation. But mathematically, it's still not good enough. You keep taking finer and finer divisions. You take how far you went in a shorter and shorter span of time, multiply by how many of those spans you need to fill up an hour, and that tells you in that very short period of time how far you went. It's still not your instantaneous velocity. Your instantaneous velocity is what happens as you let that distance go to zero. If these average speeds are converging to something, honing in on something, that's your instantaneous velocity. That's where mathematics comes in. That's where calculus comes in. You have to take what we call the limit. No actual physical positive amount of time will give you the instantaneous velocity. Only what those velocities tend to as the time gets shorter and shorter. So Newton invented calculus exactly to study these. They're called derivatives or velocities. And the velocity is what I've just described when you use distance. If you replace distance by velocity and you take these limits, you get acceleration, how fast the velocity is changing instantaneously. So that was his first law, F equals ma. F is going to be given in just a minute. M is just the amount of stuff we have. A requires differential calculus to make sense of. Now let's go to F. This is the other half of calculus that Newton invented, was required to understand the F. So F was force, in our context here, gravitational force. So Newton posited that two things of mass attract each other by what was called the inverse square law, so proportional to 1 over the square of the distance between them, and then times how much mass there is. Okay, that's this little particle here and that little particle there. But what we want to understand is how the Earth attracts the moon. or how the sun attracts the Earth, or how the sun attracts Mars, or Mercury. Well, the Earth isn't a particle. It's a whole bunch of particles smeared all over what makes up the Earth, and likewise for the sun. So we have all these individual particles attracting each other, but now I've got to add up all these contributions on all those particles. And again, it's convenient, as Newton did, to take a mathematical abstraction and turn these particles into a continuous medium. So now instead of adding up a bunch of contributions, we're actually doing the other half of calculus, which Newton invented. We're integrating all the contributions of all the sun particles on all the particles of the Earth to get an overall force law. So that was the F equals ma. He then studied the consequences of this law, and for that we get to go back even further to Kepler. Kepler had noticed that the planets move around the sun in what are now called conic sections. And the reason they're called conic sections is you take this double cone here and you cut it in various ways by a plane. And depending on what plane you use, you'll get different figures. For example, this plane, which is perpendicular to the axis of the cone, if you will, gives a circle. This plane gives an ellipse, and here I have, I don't know, half of a hyperbola maybe. If I cut parallel to one of the sides, I'd get a figure known as a parabola. These are conic sections. And Kepler had observed experimentally that the planets rotated around the sun in conic sections. He observed some other laws too, which I won't go into. That was an experimental fact. Newton, after he'd written down F equals ma and figured out differential calculus to make sense of the a, and integral calculus to help him compute the f, was then able to, by mathematical derivations, establish all of Kepler's laws from the F equal ma and his gravitational force together with integral and differential calculus. So this is a great example of the interplay between physics and mathematics. We had a physics problem. How do the planets move around the sun? How does the moon move around the Earth? The answer was we have some physics concepts, and we put those concepts into mathematics, which at the time didn't exist, but fortunately Newton was a good enough mathematician to invent them. You know, I never know if one should say invent or discover, but anyway, whatever. These laws. So he was acting both as the physicist to write down the law of gravitation and the fundamental F equals ma, how forces act on bodies, and then he invented the mathematics in order to make sense of that equation and study its consequences. Okay. Maybe the most famous example of the interaction between physics and geometry is Einstein's theory of general relativity in its relationship to curved or Riemannian geometry. So after he had formulated special relativity, Einstein spent about 15 years trying to generalize it to what's now called general relativity, and he kept searching for the right mathematical context in which to put his theory without great success. Finally, one day he explained to one of his mathematician friends what he was trying to do, and this friend said, oh, well, the mathematicians already did that. That's just Riemannian geometry. Riemann 50 years ago figured all this out. This is what you need. And indeed, several weeks later, Einstein had general relativity. Also, several weeks later, the leading mathematician of the day had a version of it too. So once Einstein realized, or somebody explained to him, what geometry already existed, it was exactly the geometry with a slight twist because it's physics and not mathematics that he needed in order to formulate general relativity, and then it all came. So this is one the mathematicians are quite proud of, needless to say. The next one goes back to the 19th century. It had been observed experimentally that if you took a gas, say like hydrogen, and you shined a white light, so a light with all colors through it, what you saw on the other side wasn't white light. there were certain frequencies that were absorbed by the hydrogen. So when you made a graph of the light coming out the other end, these were dark lines because there were no frequencies, there were no light at those special frequencies. And it was always the same. If you shined a light through hydrogen, you always got the same absorption lines. If you shined a light through helium or some other gas, you get different absorption lines. And those lines were characteristic of the material you were shining the light through. Okay, that was an experimental fact, had no basis in physics. There was no theoretical explanation for it. Well, in the late 19th century, Hilbert, our mathematician from general relativity, was studying spaces which now go under the name of Hilbert spaces, and he was studying the way they can be transformed onto themselves, like rotated around or scaled up, operators acting on a Hilbert space. And in studying those operators, he noticed they had characteristic numbers associated with them. He was German, so he called them eigenvalues, eigen for own. And he then, now I don't know how much, I'm not enough of a history of science scholar to know how much credit to give Hilbert at this point, but let's say it this way. Hilbert then said, you know, this reminds me of the spectral lines of hydrogen. There's something in common here between these numbers associated to my operators and these characteristic frequencies that are absorbed by hydrogen. So I'll call this whole theory the spectral decomposition of my operator. Okay, that's 1880. Well, finally, 1930, the spectral lines of hydrogen were accounted for through quantum mechanics. And guess what? In quantum mechanics, the way you think about things is you have a Hilbert space, and things like hydrogen are operators. And guess what? The spectral lines of hydrogen are explained by these characteristic or spectral decomposition of the operator that goes with hydrogen. So did Hilbert really know that was coming? I don't know. But as mathematicians, we can pretend he did. The last one is a much more recent example, and in fact took place here at Stony Brook, and one of the participants is here in the audience, so he'll correct me if I get it wrong, or maybe even if I get it right. Gauge theory and the mathematics of principal bundles. So here we have two Stony Brook scientists, C.N. Yang of the Institute of Theoretical Physics and Jim Simons, head of the math department. Yang is explaining to Simons, I think over and over again, what he's doing in physics, and Simons is understanding some portion, but maybe not too much. And then one day, Yang starts, as Jim recounts it, starts in on this subject of this is the latest thing, this is what he needs to understand, and here's how he's going about it. And Jim says, wait, stop, don't do that. And he says, why not? He said, because the mathematicians have already done it. So what Yang was struggling toward, and what the physicists now call gauge theory, so this is what, early 70s, I guess, late 60s, had been worked out by the mathematicians in the 30s and 40s and 50s. Now Yang had a very interesting response to this, which I'm not going to tell you now. I'll cycle back to it later at a different part of the story. But anyway, needless to say, this is really the starting point of the twist, the new relationship between mathematics and physics. It took on a completely different quality, growing out of this understanding that what the physicists were struggling toward in gauge theories, which they wanted to describe the forces that work inside the nucleus, was closely related to things that were close to the heart of mathematicians. Okay. Now I'll give you the mathematician's view of physics, and hopefully the physicist in the audience won't correct me too loudly. In some sense, physics is easy to describe. So first of all, I should say, I'm not talking about all of physics. I'm talking about what now goes under the name of high-energy theoretical physics and used to be called particle physics. There are lots of other kinds of physics that I'm not trying to describe and don't come into this story. So this is the physics of which asks the questions, what are the fundamental constituents of the universe, and what are the fundamental laws they obey? And the goal of physics is to have some construct, some way to compute and get answers to questions like, if I take two elementary particles of this type and I shoot them into an accelerator, what's the probability that I'll get out two other particles at certain angles? Notice it's probabilities. That's all you can hope for in physics. Nevertheless, that's it. And they're happy to take any construct that will produce for them a method of making these predictions. And the ultimate test, of course, is they write down a theory, they make their computations, and they say the chances, the probability that if you do this, you'll get that out at the other end, or such and such. And then they go into the laboratory, CERN or Brookhaven or wherever, and they do the experiment, and they see. And if it corresponds to what they predict, great. If it doesn't, they throw that one away and look for another one. All of mathematics, turns out, will feed into the maw of physics. Physicists are happy to use anything as long as it lets them compute something that they can go and check. Well, of course, another part of our story, to just foreshadow a little bit, is as the relationship between mathematics and physics has changed, the relationship between theoretical physics and experimental physics has also changed. And those aren't unrelated. Okay. That was the easy part. What is physics about? That's what physics is about. What is math about? That's a tougher one. So here's the best I can do. Mathematics is abstracted and generalized from physical reality and human capability. Well, lots of things fit under that description, so this clearly isn't really a definition of mathematics. But let me take a couple of examples of what I mean to try to give you a little bit of feeling for it. So we can count. We can all count. One thing that leads to is several branches of mathematics come out of our ability to count. One that comes out is write down some kind of mathematical structure and try to count how many of them there are. For example, in combinatorics and probability, how many ways can you choose 5 balls from a set of 25? That's a combinatorial problem. Maybe closer to our mathematical heart and also more related to what's coming. Let's look at graphs. So a graph has vertices, these are these black dots here, and edges. These are these red things. Each edge connects 2 dots, but as you see, the dots are allowed to be the same. So that's a graph with 4 vertices. How many graphs are there with 4 vertices? Well, that's not a hard problem to solve. How many graphs are there with 10 vertices? Slightly harder, but also can be done. How many graphs are there with n vertices? Mathematicians like the number n a lot. And what happens when n goes to infinity? Now there's a mathematical question. How fast does the number of graphs grow as n goes to infinity? So this is all abstracted out of very simple geometric pictures and our notion of counting. Another area of mathematics that comes out of counting is called the number theory. So once you can count, you have the counting numbers, 1, 2, 3, 4, 5, 6, 7. Pretty soon you notice that some of those counting numbers can be made out of earlier ones by multiplication, like 6 is 2 times 3, but 7 can't be made that way. So 7 is called prime. The other numbers are called composite. Okay, fine, we have primes. How many primes are there? Well, that was solved quite easily. There are infinitely many primes. They go on forever. There isn't a biggest one. Okay. How many primes are there less than 100? Well, you can write down a table and figure it out. How many primes less than 1,000? Again, a longer table, but you can figure it out. Computers can probably go up to, I don't know, 10 to the 10th or 10 to the 9th or 10 to the 8th. But now, here's where mathematics starts to come in, the abstraction and generalization. How many primes are there less than the number n? Well, there can't really be a formula for that. It's not too hard to see. But how does it grow as n gets bigger and bigger, as n goes to infinity? Well, there's some beautiful answers to that question. And the leading term of the growth is now completely understood. And the next order term in the growth is conjectured. And that's the most famous problem in mathematics today, I would say. And it's 150 years old. We don't know. So simple extrapolation and generalization out of counting leads us to primes, and then the question of how many primes, and to what's called the Riemann hypothesis. All right, well, that's one branch of mathematics. We're not so concerned with that here, though it does, I don't want that yet. It does come in. We'll be more interested with geometry and topology, which I'll talk about in just a minute. Now I want to cycle back to Yang's response to Simon's saying, wait a minute, the mathematicians have already done it. It goes under the name of principal bundles and connections and curvature. We got it all figured out. He said, according to Jim, why would mathematicians ever do that? And that's a deep and interesting question. Why do mathematicians ever do what they do? Another example, I was listening to one of the leading theoretical physicists 10 years or so ago at giving a talk, and he said, you know, we got to this structure and we realized we needed a different kind of geometry, so we started trying to develop it, and then we found out, somebody told us, that it had already been done by the mathematicians 10 years ago. Lawson and Harvey had done it. Well, Lawson is Blaine Lawson from Stony Brook. It's called calibrated geometry. And then he stopped and he said, now, I don't know why Lawson and Harvey were studying this. And he paused and he said, in fact, I never know why mathematicians study anything. So even our closest cousins, the physicists, don't really know why we study what we study. And I guess I'm not sure I know either. But aesthetic considerations drive, to a large part, why we study what we study. Now, these are aesthetic not in the sense of this painting is beautiful, but you will hear people say, what an incredibly beautiful theorem, what a great idea, what an elegant solution, what a powerful technique. That's part of it. Elegance is part of it. Simplicity is part of it. Connections to other parts of mathematics, power, are part of it. Connections to other disciplines, physics, engineering, can be part of it. But you can't really say ahead of time what's going to turn out to be interesting. You start thinking about these things because they look like they might be interesting, and if they turn out to be fruitful and rich subject, then you'll be studying them, and lots of other people will see how interesting what you're doing is, and they'll start doing it, and that's why we do it. We have no goal in mind except to understand these structures as we spin them out, building on what we already know. So why do mathematicians do what they do? Well, anyway, we do. And the unbelievable thing is, it's relevant. We do this stuff for their own intrinsic, internal reasons because we're interested in them. And lo and behold, as Wigner said, in the 40s, I guess, what accounts for the unreasonable effectiveness of mathematics and physics? Why is this what the physicists need? Why is it what anybody needs? Well, it is, and that keeps us going. I mean, it's clear why biology at a fundamental level becomes chemistry and why chemistry at a fundamental level becomes physics. But why does physics become mathematics? Or does it? Maybe this is just the only way we've been able to figure out how to think about it. But it's certainly been the most effective so far. And the deeper you get into the physics, so the higher and higher energy, the deeper down into the elementary particles you go, it seems the more sophisticated, elaborate mathematics you need. So, just a picture. Not really supposed to understand this. I pulled it off the internet to show you that physics and geometry have something to do with each other. You see this beautiful couple of, this is the universe, right? And this time is going forward and somehow it's curved. That has to do with the rate of expansion of the universe. So on. I'm not going to try to explain this to you. I just wanted to put it up. It's a pretty picture and it shows some relationship of physics and geometry. Okay, well, I told you the part of mathematics that we were really talking about here is geometry and topology. I've talked about how counting leads to number theory, combinatorics. Topology and geometry derive out of our perception of physical objects and our visual intuition. And there's a funny thing about geometry. When you start studying geometry and topology, you're not satisfied with the things that you can actually see, you know, these things in three-dimensional space. Suddenly you're studying not only surfaces in three-dimensional space, but spaces of all dimension, none of which a mathematician can see any better than you can, but we understand how to manipulate them, work with them, concentrate on the kind of properties that are relevant for whatever problem we're trying to think about. Let me try to give you a brief introduction or description of the difference between topology and geometry. And I started with the roots: geo, earth; metry, measurement. So geometry derived from probably the Greeks, I guess, measuring things on the surface of the earth. So they had distances and angles, and geometry is the study of spaces in which those concepts make sense. Topology, study of form. So if you have to compare the two subjects, you imagine geometric shapes as made of steel. They have fixed distances and angles and volumes and areas, whereas in topology, none of those concepts make sense. You're only interested in the form of the thing. You're free to deform it around, stretch it. If you have taffy, it doesn't have a length. You can stretch it pretty much to any length you want. If you have a steel rod, it has a length. So a steel rod is a geometric object. Taffy has only got topological properties. Now, there are, of course, intimate relationships between topology and geometry, and I want to try to show you one. But before I do that, let me show you a simple interplay between topology and physics. This has to do with the notion of right-handedness in space. So let's not cut off our right hand. Let's make a plaster mold of our right hand. And then we're free to move it around in this room anywhere we want. No matter what we do, we can never bring it back here and make it look like our left hand. It looks like our right hand always. Now, if we look at it in a mirror, it looks like our left hand. Suppose I'm allowed not only to move this plaster mold around the room, but anywhere in space. Could it ever come back and look like the left hand instead of the right hand? Well, if you ask that question about mathematical spaces, the answer is some spaces allow you to flip right and left, and others don't. Okay? If the space were really this room, then we couldn't flip right and left. I forgot to make a slide, but there is a famous example, it's easiest to see down a dimension, where right and left are flipped. So right and left here are going to be thumb and forefinger now, because I'm on the plane. I'm in a surface rather than three space. And if I make a cylinder like this, it's pretty clear if I take right and left and move them around, if I take right and move it around, it just comes right back to itself. But if I work instead on the Möbius band, right comes around and now gets flipped over. Did I do that right? Yes. Which is equivalent to left. So on the Möbius band, try it at home if you didn't see that. You can flip right and left. And there are three-dimensional spatial analogs of the Möbius band where you can take a cast of your right hand, move it through space, and come back, and it looks like your left hand instead of your right hand. Well, what about our universe? It's a nice three-dimensional space. Which kind is it? Well, for a long time, the answer wasn't known, and then it was T.D. Lee and Yang, I guess, who discovered that under one of these forces they were studying by gauge theory, when certain particles decayed under the weak force, they could spiral this way or they could spiral that way, and they didn't do it equally often. So they spiral slightly more this way than that way. So in fact, there is a handedness. The universe has a handedness. You can't take the right hand, move it around the universe, and make it into the left hand. You can distinguish right and left. You can tell somebody on Mars what you mean by your right hand. This, of course, is assuming the laws of physics are uniform through the universe and so on. Not an unreasonable assumption. So the universe is not one of these Möbius band type three-dimensional spaces. And that's a simple example of the interplay of mathematics and physics, and actually topology in this case. Okay, now I want to talk about geometry and topology of surfaces. And the fundamental concept in geometry is the idea of curvature. So let's see if I have a slide of curvature here. Yes. So I've drawn little pieces of surface. The top one is a cap-shaped piece, and that turns out to be positively curved. The middle one is a saddle, And it's got negative curvature, and the bottom one is, even though you might be surprised by this, it's flat. It has no curvature at all, because if you cut it open, you can open that sheet of paper out, and it's a flat sheet of paper. Okay. So that's curvature for surfaces, and it turns out that this curvature is related to the topology. So let me go here. Suppose I have a topological sphere. So it's not now it's not a geometric sphere, so it's not round. It's just something that can be deformed back by pushing and pulling to make it a sphere. And this one, you see, has some positive curvature over here, and some more over here, and some negative curvature here. This curvature isn't an arbitrary function on the surface. If you do this integral, adding up like Newton taught us, of the curvature over the entire surface, you always get the same answer, 4 pi. Because this is always the same topological surface. So this number is a topological number. It doesn't change as you move the metric. The curvature, as you move the metric, can change drastically, but always with this constraint that it has to add up to the same thing. Well, you can talk about other surfaces. They're not just spheres. Here's the torus. And this time, well, again, you see some regions out here of positive curvature, and if you look in toward the middle, you'll see a little saddle region. So it's negative curvature, and when you add up the curvature or integrate it around the surface, in this case, you get 0. And you can continue. There's 2-hole tori, and the integral is always minus 4 pi. 3-hole torus always gives you minus 8 pi. So we have an interplay here between geometry and topology. The topology is the number of holes, which tells us what these integrals add up to, and the curvature is the geometric quantity, and it's constrained by the topology. Okay. Yeah, so that's called the Gauss-Bonnet theorem. By the way, generalizations of this theorem are crucial in the application of, well, they're crucial in mathematics, but they're also crucial in the application of mathematics to physics. Okay. All right. So what Riemann did in the 1860s was generalize this notion of curvature from surfaces to higher dimensional shapes. It becomes much more complicated, but he not only formulated correctly the notion of curvature in higher dimensions, he showed that it was really the only interesting local property of one of these metric spaces. And this is the geometry from the 1860s that Einstein needed in the 1920s to finish off general relativity. Okay. So that's my brief description of what mathematics is, and in particular geometry and topology. So we've talked about physics. We've talked about mathematics. Let's now talk about the interaction between them. And I'll go back to the turn of the 20th century when quantum mechanics was being formulated. It took a while. It took, I don't know, 25 or 30 years before they had it right. But once they had it right, it was based on Hilbert spaces and the operators, which Hilbert had been studying 20, 30, 40 years earlier. Well, they didn't stop there. So this is solidly mathematical, beautiful mathematical theorems, beautiful mathematical context for quantum mechanics. Well, then the physicists wanted to understand quantum field theory, how particles interact with each other, how new particles are born, how particles interact with fields like the electromagnetic field. And this was growing up starting in the, I guess, after the war in the 40s. And the beautiful computational scheme has been arrived at now, but there's no mathematical foundation for this scheme. It still sits out there in thin air, but it computes beautifully to 10 decimal places things that you see in the accelerator. So there's no doubt that it's correct, and there's no doubt that these artistic methods that physicists have for dealing with quantum field theory, in fact, must have some reality in mathematics. We just haven't found it yet. Well, quantum field theory really hit its high point in the, I don't know, mid-70s, I guess, when they had formulated, through gauge theories, what's now called the standard model of physics, which accounts for all the known forces except gravity, all the forces that act inside the nucleus, and the electromagnetic force, which gives us light. It did not include gravity, and there seemed to be essential fundamental stumbling blocks that keep it from including gravity. So physicists had to look beyond quantum field theory, and the current leading candidate is something called string theory, which is even further out than quantum field theory, beyond mathematics. Though many of the arts that they learned in quantum field theory and from quantum mechanics, they now apply to string theory, and they have a beautiful basket of techniques that they use, none of which have any mathematical meaning whatsoever. And in fact, even what string theory is doesn't have a mathematical formulation. Quantum field theory, I think you can give one to. Anyway, that's a brief history of physics over the last 100 years. Quantum field theory tends to be done using what are called Feynman diagrams. There are these graphs again. You think of the ends of the graphs as being particles coming in, they interact with each other, and then they go out. So you imagine this as being something that might happen in an accelerator. You shoot in two particles, they interact again, here and here, and then a couple of outgoing particles come out. You try to sum over all possible ways that this could happen. The trouble with the mathematics is that as you bring these interaction points closer and closer together in space and time, the mathematical integrals, back to Newton, that you're trying to do blow up, become infinite, and you have to somehow account for that. And there's no completely rigorous way of doing that. So these math integrals don't converge. Nevertheless, as I say, physicists have developed these techniques, non-rigorous techniques for dealing with these infinities and getting answers that agree with experiment to enormous precision. Okay. In string theory, these Feynman diagrams, these graphs, are replaced, so particles are replaced by little strings, which string theorists would say vibrate, and therefore these interaction diagrams are replaced by something that goes under the name of a world sheet. So instead of having two particles come in, I have two little strings coming in, and they interact, and then there's two little strings coming out, and the topology of this world sheet is crucial, and you have to integrate over all possible topologies. Notice one advantage of this is that singularity which existed in the Feynman diagram has disappeared. So that's one nice aspect of string theory. Another nice aspect of string theory, which the physicists love to emphasize, is that it predicts gravity. Well, of course, they're several hundred years late in that, but nevertheless, it's a post-addiction. They're quite proud of that. So as we saw, string theory is immediately going to bring in this topology and geometry of surfaces, because that's now what Feynman diagrams are. But in fact, it brings in much, much more sophisticated mathematics, because these theories only work if space is 10-dimensional. Not 4 like we always expected, but 10. And those 6 of those 10 are wrapped up in some really little, very interesting mathematical shape, and they turn out to be some of the most studied and well-known 6-dimensional shapes. So in doing string theory, you find yourself using some of the most beautiful and sophisticated parts of mathematics. Well, there are problems with string theory. One is the energy scale at which you will see stringy phenomena, that is, where you could detect whether or not particles are particles or strings, far beyond any accelerator we could possibly build on Earth. In doing string theory, as I said, the string theorists are guided by quantum field theory and to some extent math, and I want to talk about that a little bit more. But they're far beyond any existing mathematics. So they're really out there. So as I said, the required math hasn't been created, but here's the interesting twist. String theory and quantum field theory, even though the techniques that are used in the subjects are non-mathematical, give us predictions, or maybe we should say conjectures, about classical mathematical objects, those objects that Riemann introduced us to. And they say, this one over here and this one over there, which you thought had nothing to do with each other, you never suspected they were related, in fact are intimately related through this quantum field theory, and things you can compute over here have to be equal to things you can compute over there, unlike anything we've ever seen before. Well, these kind of predictions, conjectures, have been driving mathematics. If you go around almost any mathematics department on seminar day, 9 of the 10 seminars in geometry and topology can be traced back fairly directly to questions coming out of this sort of physics. It's just come to dominate the way we think about geometry and physics these days. And lo and behold, sometimes we compute on this side, we compute on that side, and it's exactly what the physicist said. Well, reactions to that vary. The physicists take the position, this is the validation of string theory. All right, so we can't do experiments in laboratories, but we can do experiments in mathematics, and you have become our experimental physicist, and you are verifying our theories. That's one attitude. The mathematicians take an attitude of extreme frustration. Even though we can compute here and we can compute there, one senses that there is a deeper underlying connection that we don't have access to. It's not just by happenstance or miracle or accident that these things are happening. They're happening for a reason, and that reason is a deep mathematical reason that we don't understand. Well, that's where the Simon Center, well, okay, so what accounts for the unreasonable effectiveness of physics and mathematics? Why are quantum field theory and string theory giving us these incredible conjectures? Well, that's where the Simon Center is going to work. So these are fundamental issues driving mathematics and fundamental issues for theoretical physics. They need the context. They're really out in Never Never Land with no support, and they are in danger of falling in any minute. They need the mathematical support, the context. We need to understand, we the mathematicians need to understand what this insight, quantum field theory and string theory, through non-rigorous methods have brought us. What is the mathematics? These are just two faces of the same thing. Now, there are lots of places where first-rate mathematics is done, lots of places where first-rate physics is done. Often they're the same place, but no place where it's explicitly part of the goal of the institution to bring together the mathematicians and the physicists who are interested in these connections, who can talk across the gaps, stimulate across the gap, or be stimulated by what happens on the other side of the gap. That's the purpose here at the Simon Center. Going to bring a bunch of mathematicians, a bunch of physicists with these common interests together, throw in a bunch of coffee, throw in some good food, give them time and space and a nice environment in which to work, and shake it all up and see what falls out, and hopefully we'll make some progress on these fundamental questions that are driving both mathematics and physics, and if we do, that will be a great success. Thank you.